Okay, calculus. A really special day today as we talk about differentiation formulas. And the first one is talking about a constant. So suppose that you have a function equal to constant, say f of x is equal to 4. Or, say the graph y is equal to 4. That's a horizontal line that passes through 4. And if you think about the derivative is going to be 0. So therefore, the derivative of a constant is 0. In this situation, you have a line of x. And so since the derivative represents the slope, the line x has a slope of 1. As you have a constant times x, that constant in front, it represents the slope, kind of like y equals mx plus b. Whatever m is determines the slope. So the derivative of a constant times x, the derivative of that is simply just the constant, whatever it is. So the big question is, what if we come up with x to the power? Now, you guys have worked through some challenging situations in your work. For example, what do you deal with when you have, say, x cubed minus x squared? And what about if you have 1 over x plus 2? What if you have the square root of 3 minus x? You're finding those derivatives. Those are challenging. We're going to look at easier ways of finding those derivatives. And so what we are going to do is we are going to show you the power rule, otherwise known as the derivative for the function f of x equals x to the nth. And we're going to show you how we come up with the formula. This is really fun to go through. I enjoy going through it with a number of students during class every year. But in this situation, I don't get to do it with you. You have to kind of watch it, but hopefully you catch up on my enthusiasm. Remember, it's the limit as h goes 0 of f of x plus h, so it'll be x plus h raised to the nth power, then minus f of x, so minus x to the nth, divided by h. That's what we want to simplify. That's what we want to simplify, okay? So if we go ahead and try to expand this a little bit, what we're going to get, and it's very important that you focus on this whole x plus h to the nth. That's what I'm going to focus on expanding right now. I'm going to bring you back to something called Pascal's triangle. And we looked at this Pascal's triangle last year as we talked about the binomial expansion. So if we have, say, I'll just do this example here. Suppose we had x plus y to the 5th power. Well, what you could do is you could look at this row, because it has a 5 as the second number that tells you you're going x to the 5th. And we tell you have x to the 5th, and then you have x to the 4th, y. You would have x to the 3rd, y squared. You would have x squared, y cubed. You would have x, y to the 4th, and then you would have y to the 5th. And these tell you your coefficients. So it's going to be a 5x to the 4th. It's going to be a 10x cubed y squared, 10x squared y cubed, and then 5, and then 1. And so that's how we expanded that so quickly. Well, we're going to do the same thing in this situation. We're not going to be able to expand it all the way because it's to the nth power. But what I want you to notice is, again, 5 is this exponent, and 5 is this coefficient there. So that's really important to keep in mind as we look at this expansion. We have the limit as h goes to 0 of, we'll start out with an x to the nth, and then we'll get an x to the n minus 1, and we'll pick up an h. And then we'll have x to the n minus 2, and we'll pick up an h squared. So on and so forth. You'll continue to have these things until at the very end you get an h to the nth, and then minus x to the nth, and that will all be over h. Now, what about your coefficients? Well, this first coefficient here, we start with a 1, but then we have whatever n is goes right there. Whatever the power is, that ends up being the coefficient. And then after that, it's tough to tell what coefficients you have, but I'm just going to put a c sub 1, and you'll just generate other coefficients as you continue to go on. But we do know that that second coefficient is n. Watch what happens now. This is absolutely gorgeous how this works out. The x to the n's cancel. So remember, everything that doesn't have an h should cancel. So you see those x to the n's cancel. Limit as h goes to 0 of n times, whoop, don't go away. Limit as h goes to 0 of n times x to the n minus 1 h plus c sub 1 x to the n minus 2 h squared plus da 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 h to the nth all over h. Everything now has an h. I can divide the h off, and I'm left with n times x to the n minus 1. That first h disappears. But everything else, so I got c sub 1 x to the n minus 2, and then I just have one h instead of two of them. But everything else is going to have an h. The last one will have an h to the n minus 1 power, but they're all going to have an h. So notice, if you finish this off by letting h go to 0, the h goes, you know, we plug it in there and there. These all go away. Everything that has an h go away, and you're left with the derivative is equal to n times x to the n minus 1. That is your power rule. F prime of x is n times x to the n minus 1. And this is absolutely awesome. And here's why. I'm going to give you an example here. Suppose that the function is equal to, say, 8x. I'm sorry, x to the 8th. What that means is the derivative, well, she said the derivative rule is n times x to the n minus 1. What that tells us is you drop the 8 in front and you subtract 1. So it's 8x to the 7th. That's the derivative. Suppose you have a function is equal to x to the 5th. Then the derivative is 5x to the 4th. We'll do a tricky one. Suppose that f of x is x to the 3/2. Well, then the derivative is, dump the 3/2 in front, x to the 1/2. It's amazing how quickly you can find derivatives. Notice the exponent gets reduced by 1. What if you have a coefficient in front? No big deal. F of x is equal to 12x cubed. So f prime of x is, that 3 dumps in front, 3 times 12 is 36, x squared. Done. Derivatives all of a sudden become super easy. The formal definition, which is the limit, is h goes 0 of f of x plus h minus f of x over h. We don't really need to use that much anymore. We don't need to use it that much anymore. So let's try some examples here. Differentiate the following functions using the power rule. So f of x is equal to 5. You know the derivative of a constant is 0. But I'm going to show you why. Look at the next one. This is -8. If we write it as x to the 0 power, watch what happens. You drop that in front, and you get f prime of x is 0 times -8 times x then to the -1. We all know that 0 times anything is 0. Look at the next one. You have 4x to the 1 power. If you drop this 1 in front, you get f prime of x is 1 times 4 is 4. X to the subtract 1, you get 0. And anything to the 0 power is 1, so you just get 4. So notice how the power rule works in these situations. The derivative of 4x is just 4. So what is the derivative of -3x plus 5? Well, -3x, the derivative is -3, and 5, the derivative is 0. So the derivative is just -3. This one, f prime of x. I dump the 2 in front, and I get a 10x. The derivative of 10x is just 10, and the derivative of negative 3 is 0. So there is my derivative. All of a sudden, since we made this super easy, we can start to look at more. I'm going to do one more for you just because it's so fun, and then we'll get back to our other piece. But look at letter K. Imagine trying to do the limit as h goes to 0 of f of x plus h minus f of x all over h. That would be super tough. But what we can do is we can simply find the derivative. Derivative of 2x to the 7th is 14x to the 6th. Derivative of 3x to the 6th is 18x to the 5th. Derivative of 2x to the 5th is 10x to the 4th. Minus 4x cubed plus 3x squared plus 12x minus 10. And the derivative of 1,943,789,432, the derivative of that is 0 because it's simply a constant. So there you have your derivative. It is beautiful how quickly we were able to do that using the power rule. So let's get to some that are slightly more complicated. Look at f. And what makes this complicated is that it's not written as a power. So I'm not going to write the derivative yet. Notice in my notation, I'm just writing f of x. So I'm not writing f prime of x yet. I have 8x to the 5th minus 3x cubed. I'm going to write this as plus x to the negative 2, and then minus x to the 1/2. So I just rewrote it so I can understand the nature of the exponents better. Now I take the derivative. The derivative of 8x to the 5th is 40x to the 4th. The derivative of 3x cubed is 9x squared. The derivative of x to the negative 2 is negative 2x to the negative 3. And the derivative of negative x to the 1/2, I drop the 1/2 in front, and I subtract 1 from the numerator, and I get a negative 1/2. So notice that up front, I put this prime symbol. That means I actually did take the derivative. Now I need to rewrite it so that it doesn't have negative exponents. 40x to the 4th. Sorry. Minus 9x squared minus 2 over x cubed minus 1 over 2 roots of x. There's your derivative. So I know it took a while, but that's a lot better than using the formal definition, which is f of x plus h minus f of x over h. Look at this guy. I'm going to rewrite it as negative 3x to the 5/3. That's negative 3x to the, negative 5/3 power. So f prime of x, I drop the negative 5/3 in front, times that negative 3x, and I subtract 1 from the top. So negative 5/3 minus 3/3 is negative 8/3. So f prime of x is, notice the 3's will cancel, the negatives cancel, and we get 5 over x to the 8/3. I would encourage you, if I have the square root of x, I always write it like that in the denominator. But otherwise, I tend to write it as, using a rational exponent. A lot of times, the easier way of just keeping track of it. Okay. Here, next one, letter H. So f prime of x is equal to, we drop that 6/7 in front times the negative 2/5, x to the, then I subtract 1 from 6/7. So minus 7/7, or negative 1 over 7. And we get negative 12, I get 35, I get x to the 1/7 power. And that's the derivative. It's so important that it's written as x to the nth power. This is not written that way. It's not. You have to write it so it's x to some power. I've got the negative 2 on the outside. I'm first going to write this as f of x is equal to, I've got the negative, and this is 1 over 3x. So I'm going to write it as x over 3, and that's raised to the negative 2. Or f of x is negative, and this is going to be 3 over x squared. Or f of x is equal to negative 9 over x squared, or negative 9x to the negative 2. So notice what we had to do just to be able to get it in a situation where we can now use our power rule. Can't use the power rule at the beginning, you'll get the wrong answer. But in this situation, now the derivative is easy. F prime of x is, it's going to be an 18x to the negative third, which is 18 over x cubed. That makes it nice and straightforward. One more. Okay, we look at letter J. This one's a little complicated for people. We're going to try to make it easy. And we're done with our lesson. It's a very big day anytime you learn the power rule. It's an exciting moment in calculus. I'm going to rewrite this as f of x is equal to, I'm going to write the root of 5 times x to the 1/2. That way I see that the root of 5 is a coefficient and 1/2 is the power. Minus the root of 3 plus x to the 1/2. Now, a lot of people say, well, why don't you raise 3 to the 1/2? Well, this is just a constant, and the derivative of a constant is 0. So I know that that's just going to go away. If there was a variable involved, then I'd write it to the 1/2. It's just a constant, just like this guy over here is a constant. And we take the derivatives of those, they just go away. So f prime of x is, I drop the 1/2 in front, times the root of 5, times x to the negative 1/2 when I subtract 1. The derivative of the root of 3 is 0. And then we got 1/2 x to the negative 1/2 there. So notice that the derivative is, looks like we have the root of 5 in top. We have 2 roots of x in the denominator. And over here we have 1 in the top, and we have 2 roots of x in the denominator. Those do have the same denominator, and so therefore I'm going to write it as the root of 5 plus 1 over 2 roots of x. That is the derivative. Last thing I'm going to do for you is I'm going to show you these graphs because we should always be able to confirm it graphically. The tie between the numerical analysis, the algebra, and the graphs are paramount. And I love it when you can see this happen right in front of your eyes. So I've got the square root of 5x plus the square root of 3 plus the square root of x. I've got those pieces. And I'm going to graph them. I'm going to zoom standard and look at that graph. Notice that that graph, if I trace it, notice that right here, I get a corner right down here, okay? It comes to a corner, okay? In fact, it doesn't even pick up a value until you get to the root of 3. 0 to the root of 3, you get a corner right there. So that means its derivative should not have a value there. Also, look, the slope is going to be really positive right there. So we should notice that the derivative graph should be way above the x-axis. The other thing we should note is that the slope becomes less and less and less, but it's always positive. So the derivative should always be above the x-axis, okay? But over here, it should be really, really, really big, really tall, because the slope there is really great. And then over here, the derivative should be less. So let's check that out. Let's look at the derivative, okay? We type in parentheses, the root of 5, parentheses, plus 1, and close that parenthesis on top. And we're going to divide it by parentheses 2 roots of x, close that guy off, and we look at the graph. And what happens? There it is. Look at this graph. So as I hit this trace button, this takes me one. If I press down, it moves to the next one. And you can see as I move to the right, or the left, excuse me, you can notice it starts off with a higher value. It's always above the x-axis, and then it gets to a lower value. Even if you look at the table, you know, if you can see if you have x value of -1, we have errors. But if we type a value, say 3, okay, look at the y2 value. It's at 0.93. If we go closer to the x-axis, if we type in 2, you're going to see that value increase. We got 1.1. Try 1. And we got 1.618. Try like 0.5. You can see that value get bigger. It's 2.2. Try like 0.01. And all of a sudden we got 16. Try 0.00001. And all of a sudden you got a value of 511. So you can see as you get really close to that y-axis, you can see that the slope goes way up. It's up at 511. So there's me just trying to tie some things together. Calculus is awesome. I absolutely love it. I hope that you guys are enthusiastic about it as well. There's your 20-minute video. I so appreciate your guys' work and effort. I just want you to know, again, reach out to me over video if you want to quick go over a problem together. Just clicking on that Google Meet link, we can meet over camera really quick, and I can show you what to do. Good luck. Have a great week.